Okay, so this first part is going to be all about organic chemistry and what you're expected to be learning in 2C. And so we're going to kind of be covering over a lot of different topics that kind of pertain to what should be your base knowledge of Ochem, I guess. So I do like problem 1 actually, because it kind of puts us in context of what we're doing. So at the end of the day, Ochem is just the study of carbon and its bonds to hydrogen. And everything else that happens in Ochem is basically a derivative of this. Alright, so carbon, hydrogen, or maybe what happens if you have an oxygen that becomes an ether, what happens if you have an OH group that becomes an alcohol. But at the end of the day, it's just the chemistry of carbon and hydrogen, right? So what that means though, is that when something is saturated, which is a good vocab word to know, versus something that's unsaturated. So when something is saturated, it's referring to the number of hydrogens. So if a carbon is saturated, it has bound the max number of hydrogens. Okay? And typically when that happens, it's sp3. Alright, it's a tetrahedral sp3. Okay? Now if something is unsaturated, typically it's bound to less hydrogens. Alright, it's bound to less hydrogens. Or now we can start seeing double bonds, which are sp2s. And we're seeing now triple bonds, which are sps. Right? So that's kind of the nature and the whole relationship between saturated and unsaturated. And just based on how many hydrogens you have, now you can do a whole bunch of diversity of hybridization, which is important, honestly. Okay? All right. Oh, Dan, real quick. Where's the border here? Can you
A little more to the left for you. A little more.
Yeah.
That's the border. Yeah.
How about over here?
A little more.
That's,
Oh no,
yeah.
that's too far. That's too far. Yeah, right there.
Okay. Yeah. Sick. All right. Cool. All right. All right. So, yeah. So number 1, and it's important that you guys know how to recognize sp3s, sp2s, and sps. And it's typically because they're going to have either single bonds, double bonds, or triple bonds. All right. That's where you're going to see them in Ochem. Number 5, I got kind of lazy, where it says like draw a whole bunch of isomers of C8H18. I'm not going to do that. That's going to be something for you to practice at home. However, I will say that it's also important when you start learning now about Ochem, but this is also important in transition metal chemistry. It's important to know about isomers. All right, so this is another vocab word that I think is important. What are structural isomers? And we'll cover later what are optical isomers. But structural isomers, right, this is I guess kind of number 5. Structural isomers, they have the same formula, but different atomic arrangement, I think I said. Yeah. Different atomic arrangement. So what that means in Ochem is if you have something like a pentane, 5 carbon linear structure, in theory you can also do this. Right? So these two are the same formula. This is C5 should be H12. They're both C5H12. However, they're different structures. Right? They're obviously coordinated differently. But that's very important if that's understood. Alright, cool. Does that make sense? Okay. Now, one thing that I also kind of got the vibe from our meeting is that he kind of hinted at some questions being kind of out of the blue. And so one of the questions that I thought might be important to look at is number 7. Can I erase that really quickly? So, So number 7. The number 7 in the homework problem deals with, well, it asks about boiling points. Okay. So in theory, this could be something that's kind of reviewed from Chem 2B. You know, how do we determine boiling points of stuff, right? But in organic chemistry, there's a very specific sort of rules you need, at least 2 of them that you need to account for. The first one here being, all right, well, the more carbons, the higher the boiling point. So just in general, a really good rule of thumb is if you have more carbons, you're going to have a higher boiling point. Okay? So I kind of give this example, right? You have propane versus pentane again, right? And we know that boiling point originates from the intermolecular forces that are keeping our molecules together, right? So I like to think of them like this. If you have 3 carbons, right, they pair up 3 times. Okay? Propane pairs up 3 times. This is obviously not physically relevant, but it's a good way, it's a good thought exercise to think of it. But a pentane interacts 5 times. So which one has more interaction? The pentane. Therefore, which one has a higher boiling point? The pentane. Okay? So that's like the basic rule. The other rule that I think is important to know is a linear structure has a higher boiling point than its branched isomer. I hope this also kind of makes sense, right? But let's just do a butane. And then, that's 4, that's 3. Okay. So this is butane, but one is isobutane, but they're the same structure. But if you think about it, right? If we just draw a butane again, there's 4 different connections, which is great. Okay. But now if you do the same exact thing with your isobutane, right? Look at 3, right? This carbon here in the middle, or you can think of it, this carbon here on top, is blocked from reacting with this carbon. So overall, a linear structure of the same formula will have a higher boiling point than a branch structure of that same formula. Right? Yeah. Yeah, these are some of the more fundamental, kind of random facts about organic chemistry that I kind of wanted to get out of the way first, before we start going into the more obvious things that are going to be in the exam, like nomenclature. All right. Any questions? Cool. All right. So we'll go with that. See, the one thing, if you saw, I mean, you guys aren't in 2B, but in the 2B video, I was raving about the fact that I figured this out. I can use 2 boards, basically. I can use 1 board and make it into 2 at the same time. I love this. I mean, this is... You know what? My life doesn't have a lot going on right now. I need the wins every now and then. Okay. So, the next part, obviously, here is 9B, and that's where we're going to start moving into nomenclature. Can you go from structure to name? And it's also important to go from name to structure. So the first one, we're going to go from name to structure. I think it's a little easier. So we have this structure here, this long name, 2,2,4-trimethylpentane, right? So how I like to look at these to kind of make them more standardized is step 1, you want to find your parent chain. What that means is you want to find the chain in the name, you want to find where it describes the longest chain. And it's here. It's your pentane. Right? So no matter what, we know that this molecule will need to have a pentane base. Right? So I would just try it. Yeah, pentane. Okay, that's what we know so far is a pentane. Right? Now, for step 2, we have to label our numerical positions. Right? So a really cool, part about organic chemistry, which makes it kind of interesting actually, is that they tell you where the things are. They tell you where the positions of substituents are. And in this case, because we've drawn a pentane, it doesn't really matter where our numbers go, because it'll, we can choose, we can tell it where 1 is. And so I can choose 1 to be here, and therefore 2 is there, 3 is there, 4 is there, 5 is there. And it's good practice, especially when you move on to other Ochem, to number your carbons, to make sure that the carbons you're counting is actually 5 and not 4, because a lot of reactions actually do lose carbon, which is kind of cool, right? So, and it's also a good check to make sure that you actually drew a parent chain correct. All right, so in 2,2,4-trimethylpentane, I've labeled everything. And now the final step here is to look at our substituents, right? So the tri part indicates that there's 3, and the methyl part indicates that there are methane substituents. Okay. So that says that we have 3 methanes, 1 at position 2, another one at position 2, and then 1 at position 4. So 1, 2, 3. That's it. So going from name to structure, I think is a bit more, slightly easier than going from structure to name. And all it really takes is understanding the regions of the name, right? So this is your number of positions, these are your substituents, and then that is your parent compound. And that'll actually help a lot also when you're actually doing structures the other way around. Okay, cool. Any questions? All right. You raised? Go then. All right. The next one we'll do kind of the reverse here. Now we're going from structure to name. So we're gonna. I modified 11D a little bit. So on your homework, they give you this really cool like chain-looking thing. So I think this is where I modified this. So I changed this, and then I added 1 to here. Alright, so you have this really nice long compound here. Alright, so another thing that I wasn't really mentioning here, but it's also important, it's important to know that, these corners here represent carbons, but you need to be able to take this bulky carbon structure and turn it into a linear structure. Alright, that's also something you should try to get familiar with as soon as you can, as that's important. Alright, and so what that kind of looks like, just for the record, so this is this compound. So one of the things you should do before Thursday is get as comfortable as you can with converting this to this and backwards. Okay? That's a very good skill to have. All right. I think we need the whole book. Can I raise this one? 90. Both of them. All right. This is going to be a long one, but a thorough one. All right. So. All right. Anyway, so this is basically this is going to be a crash course on organic nomenclature. Right? So step 1 in Ochem nomenclature is again identify the parent chain. We need to know, and what is the parent chain? It's the longest and continuous. Longest and continuous chain on this molecule. And so actually, you know, sometimes it can be kind of hard to see which chain is longest. And so it's okay to kind of guess and check, right? You know, let's start here. 1, 2, 3, 4, 5, 6, 7, 8. There's also, this is the 8 version, right? There's an 8. If I go from like here, 1, 2, 3, 4, 5, 6, 7, doesn't matter. But if I go 1, 2, 3, 4, 5, 6, 7, 8, 9. So far, that's the longest chain, and then I can keep checking to make sure that it truly is the longest chain. And you know, because I wrote this, yeah, the longest chain is 9. Okay, so our longest chain is 9, and so I would label them. These labels may be wrong eventually, but we're not trying to skip steps. We're trying just to find the longest chain. So the longest chain is 9 carbons. Okay, then we want to check to make sure no other group is on there. So no alkene group, no alkyne group. There isn't any of that. So this has to then be, if it's 9 carbons with nothing else, it's just an alkane, it's going to be a non. And then because it's an alkane, it ends in ane. And because there's 9 carbons, the prefix is non. Okay, so this is a non-name. Okay, cool. So our name is going to have non-name in it. Right? Now 2, this is where we're going to kind of break a little bit from what we've been doing. Now we want to ID our substituents. What are our substituents in our molecule? Right. So from here, if this is our longest carbon chain, basically everything that isn't our chain is a substituent. Right? So yeah, we can circle them. There's this guy, there's this guy, and there's this one. Okay, so we have 3 substituents. Okay. What are those substituents? Well, we have 2 methanes, and we have 1 ethane. Right? Those are our substituents. Okay, and because they're substituents, you replace the A-N-E ending with the IL ending. Okay, so instead of 2 methanes, we now have 2 methyl groups. Okay, so we do have 2 methyls and 2 ethyls. Alright. Alright, so far so good. We know it's a non-name, and we know our name's going to have methyl and ethyl. The last and final step is step 3. We want to verify our numbering. Verify our numbers. Okay. Right, because part of this nomenclature is to make sure that the numbers you're actually putting down are correct. Because there is a incorrect way of doing it. And so the way you verify your numbers is to look from either side of the chain and count to the first time you see a substituent. So in this case, we go from this terminal, we go 1, 2, 3, that's the first carbon, we encounter some methanes. And if we go from this way, it's going to be 1, 2, 3, 4. Right? And so in organic chemistry, we always want the numbers to be the lowest. And so obviously, the way you number it is based on which numbering system encounters the methane first. Basically, what is the smallest number that encounters a substituent? Does that make sense? Okay, cool. Okay. Anyway, yeah, so this numbering is correct, which is great. All right, cool. And then finally, we bring everything together, right? So on position 3, the last step. The reason why I picked this in the first place. Well, now that we have an ethyl and a methyl group, which one goes first?
Ethyl.
The ethyl group. Why?
E.
It's alphabetical. Exactly. Yeah. So it's alphabetical, right? So this compound's name is going to be 6-ethyl 3,3-dimethyl non-A. Hold on. That is the name of the compound. Right? And so, once you start, basically the only thing I really wanted to do with this problem is everything else is very standard except the one thing I wanted to stress is it's alphabetical naming, okay? When you have more than one. But yeah. Any questions about that? No? Yeah.
Is there a dash between the comma and the...
Oh, like here?
Yeah.
Yes. Yes. Do keep in mind, I'm not an organic chemist. I don't care if the organic chemistry scream at me. You can do whatever. Yeah.
Do you know Farhat's like pretty particular about like spelling and like?
Oh, that's a good question. For some, it does matter.
I think
right?
he does take off points if you spell like EN wrong.
EN.
Like,
like for the
ligands
yeah.
and stuff.
Yeah, I can see that. Yeah, like the thing though, right, is some of the mistakes are critical, right? Like if you make that an E instead of an A, it's a whole different thing, right? So some are very, very, some are very important. Ethylene diamine. Now you know ethylene diamine is because it has 2 carbons. That's the ethyl group, and then the diamine is the 2 amine groups, right? I do think it's probably particular about spelling. Yes.
If we forget which amine is the one for orgo and which one's the one for like the metal compounds, do you think he'll take off points for that, or is that like?
I feel like he will be. Yeah, I mean that's also a very easy thing to kind of pick up.
Yeah.
Yeah,
I mean, who's grading the tests?
TAs.
So, are you gonna be?
I'm not gonna grade all your questions.
You just grade one question.
I only grade one question for everybody.
Oh.
Yeah. This guy was thinking I grade all. But does that make sense?
Yeah.
Okay. Yeah. What's up?
Okay, so you're looking for the longest chain.
Okay.
But are you supposed to get like the lowest set of numbers, or like along with the longest chain?
Yeah. So this is the verified the number part, number 3. So the lowest numbers correspond to where you hit the substitution first. That's where the lowest numbers mean. Or that's where they come into play, I guess.
So like wherever there's branches.
Yeah.
Okay, because I know we have a 6 and then ethyl. I guess because it's alphabetical.
Yeah. That's okay so long as like, just follow the numbering system first. That takes priority, and then whatever is here, is just based off whatever numerical priority you put on your system.
Yeah.
Cool. Yeah.
Let's say the ethyl would be like the same distance from the 9 as the methyls are from the 1. Would you then prioritize making the 2 methyls the 3?
The priority is highest molecular weight. So ethyls first. I guess another way you can think about it is you want to see a number. If that's the case, specifically if that's the case, you want this number to be lower. So it should be ethyls.
So whichever one's bigger, if they're at like same distance, should be lower.
Wait, on the last midterm, which question did you grade?
24A, I think.
Huh?
24A.
24A. Oh, yeah.
That's the one everyone got a 0 on. That question, yeah. That was me. Hey, I was kind. I was merciful to those people.
I think you were with me, actually, now that I think about it.
Okay. Jordan, do you have a question?
When does a priority
Yeah,
come
yeah,
in? Is that you have like alcohol, carbonyl?
You mean like priority groups?
Yeah.
Yes, yeah. So they're all based off. Yeah. So I think I can go over that next. Yeah. So you're right. So that comes in when you're dealing with functional groups other than alkanes. Okay, cool. But does that make sense? Kind of a crash course in organic nomenclature. Okay. Cool. All right. So now we're kind of gonna. This is not on your textbook. This is more like a list of things you should know for your exam regarding organic chemistry function groups. Okay, so this is just a list of stuff. All right, so we're gonna talk about first thing is endings. of different functional groups. So to Jordan's question, right? What happens when you have groups that are larger or have more priority than alkanes? So different functional groups. So the whole nomenclature that you've been learning stays the same, right? The position, numbering position, your substituent name, but now the ending changes, right? So if you have an ene at the end, so a pentene, a hexene, whatever kind of ene, ene, right? This refers to an alkene, okay, which is a double bond. It's a double bond C. Okay. So then an example of this would be propene. And that's what it would look like, propene. Alright. Then you have the ending "-ine". Alright, "-ine" refers to alkynes, which are triple bonds. Okay. And an example of this would be butane. A quick note about triple bonds. I draw them like this because it's easy for me to see, but very regularly people can draw them like this. You're supposed to know that's 4 carbons in there. Okay. But be the change with me. We will start the revolution, and that's how that's how it should be drawn. But sometimes we'll draw like this. And it's annoying. Okay. I've missed points, as you can see, because of that. All right. The next one, the ending al, al. Right? This specifically refers to something called an aldehyde, which we will encounter a little later. Okay, so an aldehyde, an aldehyde looks like this, where you have, oops, that's not our group, it's an H group. It looks like this, where you have a carbonyl or a C double bond O, and then attached to a hydrogen. Right? That's an aldehyde. Right? And an example of this is something, I don't know, what did I choose? Oh, butanol. So something like butanol. Alright? Okay. Now how about if something ends in O? OL. Okay, OL. Alcohol? Yeah, alcohols. These are alcohols. You have your O, your R, and then OH, and then something like methanol. So methanol is CH3OH. Right, so there's your methanol. And then the final one that I think is kind of worth knowing is something called a diol. Have you guys encountered diols before? It's 2 oxygens. Right, so or 2 alcohols. Alright. And so I don't know, something like an example would be propan 1,3-diol, which is great. So that's propan 1,3-diol. Right? But yeah, no, there's great practice on that specific part of the homework chapter of not only being familiar with these, but also getting familiar with a whole bunch of other stuff. So highly recommend studying 15, number 15 I think it's called. And so so cool. And any questions about the ending? Yes.
What's the difference between an aldehyde and a ketone?
In what sense? Like naming wise or?
No, like how they're placed. Like Is it like a ketone just in the middle somewhere?
Yes,
Okay.
pretty much. Yeah. So so an aldehyde has an H on one side. A ketone has another R group on the other
Okay.
side. Important distinction. Yeah. Wayne and Marla, did you guys have a question?
Wait, so ketone is just like something as in if you just, fusing two different sections on the side and you have just like a double bond to an O, that's ketone.
Pretty much. Yeah.
Okay.
Okay. The last few things here that I want to kind of go over, not to belabor the point, right? But okay, so this is the endings of famous functional groups, which you'll encounter at some point, and then these are just functional groups that you should know as well. So this is an alcohol, right? This is an ether. Which I think has a really cool name. This, that's a ketone? Yes, that's a ketone. Another name that people could call it, I call it this all the time, it's called a carbonyl. You can actually use carbonyl in transition chemistry. If you recognize CO, that's carbonyl. Okay. Then of course there's your amine, single M, single N amine. Your that's an alkyne. You want that yet. Alkenes, alkynes. Okay. Alkenes, alkynes. Everyone cool if I erase this part instead? Everyone go with that? So, yeah, question.
Wait, what is the bottom one?
This guy here?
Yeah.
The dial?
Yeah, I don't think I've ever seen it.
Oh, it's two alcohols. So it's like, yeah, so typically how they look like is, this is a very famous structure where the two alcohols kind of like buttress the size of the molecule. So see how there's like 1, 2, 3 carbons? So that's a
Yeah.
propane. So a propane 1,3-diol is 3 carbons sandwiched together between 2 oxygens.
But
Or
the
2.
one and the three are like you're naming the carbon.
Yeah, 1, 3 is in, yeah.
Oh, okay.
Yeah. Yeah, the 1 and 3 are.
Okay.
Yeah. I said you wanted to.
On the homework, when I put the numbers, like, I got it wrong, because it was like, oh, like, technically they're both on the first side, because, like, you read it. I don't know if that makes
Like
sense.
if you.
Like, technically
you could
that's
also
1 and
flip
that's
it.
also 1. So I got it wrong. But, like, I don't know
Okay,
if
so
I'm supposed to number it.
so the homework said they're both 1.
Like, I only have to put propane diol. Like, I didn't have to put, like, 1, 3. Because,
Oh.
like, technically, like, they're both at the end of the chain.
Yeah. Yes, so they're correct, but this isn't wrong. You're
Okay.
just being specific.
So if I wrote that in the test,
You should, yeah, you should get the points. And then if not, you can email me. I can try to argue. I do like arguing with professors.
but we can't even see our final.
Yeah, you understand.
We can't see our final, right?
Fudge. Right, right.
You can't see our final?
We can't.
Is that on Crystal?
No, they don't have to post it.
I guess you can argue it's implied.
So they make up
But,
shapes.
Actually, once you do this, you did really good though.
Like, what's preferred? Like, I don't get points off.
Yeah. I guess the preferred way would be the you would just do propanediol.
Okay.
Yeah, you wouldn't add the 2 numbers. Because it's, what's the word? Not irrelevant, but it's, I don't even know it in Spanish, I don't know guys. It's when like redundant. It's redundant.
Because in our homework they accept like when you say like 1,3 propendial has also works instead of putting the 1, 3 in the middle. You put it in the front.
Yeah, so this is the one thing that gets really stupid about organic like nomenclature is I was taught this way. In fact, I was taught to put di 1,3-ol. right? That's how I learned it. It doesn't matter. It's the same exact thing. Same exact structure.
But do you see we can put like for like like just anything, so like we could put like 1,3 propendial or like 1,3 like methanol.
Oh, like we're up here?
Yeah, like 1 methanol.
No. The 1,3 has to describe the O. That's what you're describing.
Oh, okay.
Right. So if you put 1,3 up here, it would be wrong.
Okay.
The 1,3 has to be describing the diol.
And like because I know like you can put like stuff like hexene, like where you have hex and then the number and the E and E. But in like OWL, they also accept like you have a number and then hexene.
That one's because there's nothing else attached to it.
Okay.
So hexene would be, so you said 6 hexene, something like that?
Yeah, like
Sure.
3 hexene, 6 hexene.
Yeah, so because they accept it because you're basically just putting in that.
Oh yeah.
So 6 hexene. Now if there's something else, if you put 6 hexene, that'd be wrong.
So because it's attached to something, then you have to put the numbers.
Yeah,
together.
you have to be specific.
Okay.
So if there's no, what's it called, substituents,
Okay.
and you're just like describing where the double or triple bond is,
Mhm.
then you can put the numbers either like at the very front or like in the middle.
Yeah.
Oh yeah.
Because the whole idea here is they created a naming system that tries to make it unambiguous what you're talking about. And so if you don't have any substituents, in theory you can add your number anywhere because it's all the same.
For something like ESA, like how would you count like the carbon chain? Carbon chain when you don't like when like the carbons are disconnected.
Oh, I see. You count them separately. So, this is one of the most famous ethers. This is called diethyl ether, obviously because it's a diethyl. But the reason it's called diethyl is because you're describing 2 ethyl groups. So this isn't a butyl group. It's 2 ethyls. 1 ethyl on one side, the other ethyl on the other side. You describe them separately.
But you don't have the number in this case.
In this case, no.
Okay.
But if there was a substituent, then yeah, you would just. If there was a substituent on here, by the way, it wouldn't matter what numbering system you put on. If you put it here, then you have to give your chain a name. But that's advanced Ochem. You promise you won't see this.
We won't see like different things on each side.
No.
Okay.
No.
But if we do have a substituent, would you also
Like here. Yeah, if you had a
I see.
this
Both
substituent.
both sides will be the same.
Yeah, exactly. You
Okay.
can flip them all. It doesn't matter. So you would still be unambiguous. But once you have another substrate, or sorry, another substituent on the other side, that's when you actually start naming your chains.
Okay.
Okay. Any other questions?
Yeah.
Okay.
Also for ketone, like
Yeah.
if it's in a part of carbon chain, like where would you like denote like the number? Where you put a number at like the center of it?
No. Well, okay. So
Yeah.
pentane with the ketone. So this is called pentanone. Okay.
Oh, I see.
But it's
Two.
2-pentanone.
So do they all have like? Is it just ketone, or do they all have like an ending? Like a
They
chain?
all everyone does have an ending, but I'm only just giving you these guys. The amine one, the amine ending is literally just amine.
Oh, okay.
Uh,
And that's like the same with ether. Like you just say
ether, yeah. Ether is just ether.
So, but just ketone, you just put O and E.
Owen.
Okay.
Ketones are Owens.
Got it.
Yep. Any other questions? There. Okay. All right. Can I erase this? That was a good discussion on organic chemistry.
Yes.
Your professors wish they had that. I don't mean that. I didn't say that. Okay, the other parts here then would be the last few ones that you should know. So here's your aldehyde again. Your carboxylic acid, this is a very popular one, make sure you know this one. Your ester group. And then your amide group. aldehyde. This is your carboxylic acid. That's your ester. And that's your amide. Amide with a D. Alright, so these are some pretty cool ones, pretty good functional groups that you should be familiar with. Oh, yeah.
For carboxylic acid, do you also put an ending, a different ending?
Yes. Ic acid.
Okay.
So propanoic acid.
Yeah.
Benzoic acid. Esters are O8s. That's their name, always. Amide is the same.
Amide.
Okay. And then al for aldehydes.
And you will start counting the carbon chain from like the center carbon for like carboxylic acid.
Like here, right?
Yeah.
Yes.
Okay.
Yeah. That will automatically be chain one or carbon one.
Yeah.
For all those.
Okay. And do you still need to put like a one with like one something acid? One something big acid?
No. If you're describing specifically the carboxylic acid, it's implied that the one carbon belongs to the carboxylic acid.
Okay.
Alright. Cool. Any other questions? Just a few other ones. Two more that you will see. There's benzene. And then the final one is what happens if I take an alcohol to benzene. Phenyl. Okay. These are some decent ones here that you should be familiar with. Alright. Cool. Any other questions?
What if benzene is the substituent? Is it final?
Benzyl.
It was phenol.
Oh, there's two. So there is, you're right, there's one, so there's this substituent, and then there's just a regular benzene. Just so I don't give, well, I was gone. Just so I don't give the wrong information. I think, so one of them is called benzyl, the other one's called the phenyl. But, I don't remember which is which. Let's look it up, shall we? Yeah, okay, yeah, so just by itself, it's called the phenyl group. And then with the carbon, it's called the benzyl group.
By itself? Like, is that just a benzene?
I guess the nomenclature gets kind of weird here, because then it's like, what if you have to have a CH2 group? So benzyl, you're forced to have a CH2 group there, right? But for phenyl, it could exist like this.
Yeah.
It could also be attached to like a carbon that's attached to like ether, stuff like that. So long as if you have a CH2 group, it's called a benzyl. If you don't have a CH2 group, it's called a phenyl.
Just one CH2?
Yeah, just one CH2. I call it. It's called a bridging carbon. So yeah. All right. Any other questions? All right. Okay, cool. All right, so the next part here. It's all about stereoisomerism. There's multiple types of isomerism. So as I was saying, there's structural isomerism. There's geometric isomerism. And there's also stereochemical isomerism. There's three types. Alright, so structural. We went over structural later, or earlier. This is just same formula, different atomic connectivity. Alright, we went over structure. Now, there's also this other isomerism called geometric isomer, which is the same formula, same connectivity, but now it's different 3D arrangements. And I want to be specific about something. These 3D arrangements are not referring to R and S configuration. They're referring to the cis and trans in the two scenarios of organic chemistry. Okay. And then obviously stereochemical. This is the 3D arrangements. These are the 3D arrangements of substituents. 3D arrangements of substituents around a chiral center. Okay. This is cis and trans, and this is now the R and S configurations. Right. So there are 3 different types of isomerisms. Right. All right. So structural stuff. Again, like I said, be familiar with it. Be able to go, be able to make a whole bunch of structures from one single thing. Geometrically, though, there's 2 scenarios. The first scenario is it's describing the orientation of substituents on a cycloalkane. So, for example, yeah, we can do that. Okay, versus so notice the difference now. There's 2 differences. The first one here, the BR is facing towards us, but the CL is facing behind us, right? This is called the trans configuration, where they're on opposite sides. And they're across from each other. Now the opposite is that they're both facing towards us. They're on the same side. That's what cis literally means, same. So this is the cis configuration. But the very important thing that I want to impart on you is this only applies when there are 2 substituents. Once there's 3, it doesn't mean anything, right? Because trans and cis specify you need 2 substituents. If you can't have 3, you can't have 1. This is only 2. But this is the cycloalkane orientation. There's also another scenario which doesn't apply to stereochem. But the other scenario is now you're looking at the 3D orientation of alkenes, right? So now we're looking at alkenes. Again, the alkenes need to have it can only have 2 non-hydrogen substituents, right? So there's a hydrogen here. That's it. It can only have 2. And the 2 substituents we have are these 2 methyl groups. Right. Now on this side, again, like I was saying, because cis means the same, the 2 methyl groups are on the same side. They're kind of facing the same direction, right? They're the same side, so they're the cis version. And the trans version, again, means across, where one's going one way and the other one's going in the completely opposite direction. So this is the cis version, and that's the trans version. But these are 2 scenarios where we can use that same nomenclature, and they're both valid. Any questions on that? Good. Okay, cool. All right. So. All right. So once we get all this kind of stuff done, the last remaining part of isomerism is now the stereochemical isomerism. Now we're talking about RNS configurations. Right. So does this make sense? Can I erase this? Can I look at that? So we're going to erase basically this stuff. And we're going to stick to the RNS stuff. All right, so the first thing you need to do in all sort of stereochemical operations is you need to determine whether or not something is chiral in the first place. All right, so step one in determining RNS is determine if determine if carbon is chiral. All right. Determine if carbon is chiral. That's step one. There's two ways to determine something is chiral. The first one is probably the way that's going to help you more with RNS. The other way is a very quick and easy way, especially when you're going over but a lot of different molecules at once. A quick sort of visual confirmation can tell you if it's chiral or not. So the first thing, the more chemical way of looking at it, is all bonds on a chiral carbon must be unique. So for example, right, we have this guy here, okay? So obviously, this is the chiral carbon, but why? So we're missing one other thing actually. Right, so it's implied there's a hydrogen there, first of all, but on every single bond to this carbon is different. This one has a bond to an alcohol group. This bond is to a hydrogen group. This bond here is to an ethyl group. It's not just a carbon, it's an ethyl group, right? But this side, yes, it's bonded to a carbon, but it is unique because this is a propyl group. That's what constitutes chirality. That's the uniqueness of it, right? The other way of looking at chirality, which is a simpler way, is asking if your compound has an internal plane of symmetry. This actually is also useful for the transition metal chapter when you're talking about chiral and achiral centers. All you gotta ask, does your compound have a center of symmetry? So, this compound, for example, right? Is there an internal plane of symmetry? Yeah, it's right down the middle here. Right? Where these two groups are the same. Therefore, is that carbon chiral? No. Okay. So again, this is a quick, easy visual check. Is my thing chiral? Just draw a plane of symmetry if you can, and it's achiral. Okay? There's identical groups in there. Right, but this is more the chemical way of looking at it. Okay. Any questions? Yeah.
And having being chiral is also optical isomer, right?
Yes. Okay. Yes. Okay. Good. All right. Do you guys want to do an in-depth dive into RS stuff? Do you guys want to do that? Yeah, I have one person saying yes. Okay. All right. Well, one is enough.
Wait, what's RNS again?
Like the actual words, or like just like the actual like chemical process.
Yeah, like
I think it's German.
I mean, like what's like the process? Like,
Yeah, we can go to that. We can go to that. Yeah. I thought you meant like the actual words RNS. I'm like, I don't think it's German. I don't really know what they are. Okay. All right. So yeah. All right, that's fine. So step one was determining if your carbon is chiral in the first place. If it is chiral, then you can actually start applying RNS. If it's not chiral, don't waste your time. There's no need. All right, so step 2 though. Okay, so it's labeling substituents. Label substituents A through D. Labeling substituents, that's making me uncomfortable. It's not supposed to be. Labeling substituents A through D based on molecular mass. All right, so we'll do the hard one. We can do that. My example is from the worksheet. Okay, it's this thing. All right, so that's what we're looking at here. So step 1, can we identify a chiral carbon? It's this one, right? Are you guys gonna be good with that? Because there's a chlorine, a hydrogen, a methyl group, and then a propyl group, or ethyl group over there, right? So that's a chiral carbon. Now we need to label our substituents A through D based on molecular mass. So D is the lowest molecular mass, which is H, obviously, right? It's the lowest one. Our chlorine is our A, it's the largest one, right? But now we have to decide between our methyl and our ethyl. So one way you can think about it, yeah, that's fine. One way you can think about it is, okay, well, our first 2 atoms that we encounter are both carbons. That's not helpful, right? It doesn't tell us which one's larger. But the next bond you encounter is a CH and a CC. So when you're now considering the second atom you encounter, the carbon or the hydrogen, which one's larger? The carbon, right? So this is the B, and that's the C. All right, another way I like to think about it is imagine each of this substituent has like emotional baggage. Which one has the most emotional baggage? It's this one. And I did get an A in Ochem, so it works. You guys are all looking, oh no, I got over 100. So yeah, so this is, but does that make sense? Okay, it's a very important part that this makes sense. Okay, now the really important part, step 3. You have to make sure that D, so the label D, yeah, okay, is facing away from you, or another way of saying this is make sure it's on its dash. Make sure it's on the dashed line. Okay, this is a very crucial step to determine this. This really determines if you get this question right or wrong. So, is our H on the dashed line? It's not. Okay, so what do we do now? Well, we have to manually put our H onto the dashed line. So we see that here chlorine, the one right next to it, all we gotta do is switch them around. So literally make a new structure, whatever you need to do. Write something differently, whatever you need to do. Right, make that a manual switch, and then put something in the structure that tells you that something's, I call it the flipped version, right? That's important, that you understand that you flipped it. Okay, one of the biggest mistakes after this point is forgetting that you flipped it. Right, so make sure somewhere you know it's flipped. Okay, so great. Now everything is labeled. We had a flip, unfortunately. That's okay. Okay, so now step 4. We're gonna draw an arrow from A to D. And then if it's clockwise, it's the R configuration. And if it's counterclockwise, counterclock, it's the S configuration. Right? The way I like to remember it is that R is clockwise. It's like the right way the clock works. So R, right way, and then S is the other way. Right? So let's trace that out. Okay, A, B, C. All right, so what is that? That's clockwise? Yes, that's clockwise. All right, so that's clockwise, right? But keep in mind, you flipped it. So it's actually not R, it's S. And that's your final answer. Cool.
Why don't you draw the other way, like from A to B? Oh, A, B, C, D, I see. Yeah.
So it's not R, because you flipped it, it's S. Right, so that's why 3 is so important. Because 3 literally gives you the right answer. Now if you didn't flip it, you don't need to do the final opposite. You can just accept it as is. Okay. Does that make sense? You want to answer again first.
How would you name it?
Name.
Like, how would you name the compound?
Oh, this guy specifically?
Yeah.
Yeah, let's do it. So parent chain first. 1, 2, 3, 4. All right, that's a butane. Then we look at substituents. There's only one. This is a chloral group. Okay, and then we got to make sure that our numbering system is good. So 1, 2, 3, 4. It takes 2 to encounter the chlorine. 1, 2, 3. So our number system is good. So this is 2 chloro butane.
Do you have to put the S in front? Oh, sorry.
Yeah. Yeah.
What does like even knowing the RNS like do?
Like, what's the physical purpose of it?
Yeah.
So it comes from, actually comes from another numbering system called L&D, which all had to do with a German chemist who looked at sugars and realized that if he had a certain type of sugar, light would bend a certain way, and if he had the D version, sugar would bend the other way. That's actually where this RNS came from, is that if you put this, there's an instrument called the CD spectrometer, which takes polarized light and then optically twists it. This will actually scatter polarized light differently than the R version. And actually you physically see that. So that's where the names come from. Yeah.
Does R and S go before like cis and trans?
Oh, good question. Oh, that's a really good question. The only time you would be, okay, so a few things. One, the only time you would actually be, if you had the chance for both, would be only with a cycloalkane.
Mm-hmm.
Because then an alkene would then be something called EZ configuration. Something totally different. But anyway, whether they come before, I'm thinking of a compound. Yeah, they come before. Yeah, because this is your atomic coordinate here. Yeah, so it's 2s cis, and then that's obviously not the right name, but if it was the cyclobutane, it would be there. Okay. Very good question. Yeah.
Why did you put 2S?
Because if it's now, if it was just that, right, it would not be ambiguous because the 2 has to be in the butane, and the S is part of the 2, right? But now that we've included the cis, you want to make sure that that 2 stays where it needs to stay. So the 2S, basically the difference would just be these 2 S's are the same, they're describing the same thing, except if you didn't have this would be fine because we know you're describing that. But if you have more than this, then you have to put the S next to the position 2. Because 2 is where the stereo center is.
Okay.
Does that make sense?
Yeah.
Okay. Cool. Yeah.
And my question from before, is there ever a case where, like, I don't know, maybe this doesn't happen, but where it's like, if like the C and the D switch spots, is there ever a case where that
Oh, these guys?
yeah,
Like that?
yeah.
So, in theory, yes, but you should always just try to just do this.
Okay.
You can do this, but that gets more complicated. But you should just do that. Because typically your H is going to be back. It's going to either be forward or backward. That's typically how you draw it.
Mm-hmm. So like it could be like that, but you just have to like turn it around.
Yeah.
Kind of, okay.
It's just easier to do it this way. The rules have been standardized for this way. Unless you're like a really good 3D person, which you can see it.
Wait, so where did like the cis come from again?
Oh, there's no. This is from another question.
Oh, okay.
Yeah, so there is no cis here.
What if you flip B and C? How would you determine if it was RS initially?
That's a harder question. It's not hard, but it requires some 3D knowledge here. So if it's this, and you switched these two,
Can you just do the process again?
it's, in theory, yeah. But the way, so if I remember I did that once on an exam, but the way I did it though was I literally like, I saw it out. I drew with pencils. So the C is facing this way, and the H is facing this way. I think it would be the same, wouldn't it? You would have to account for it, switching around. Oh, see from there. Okay, if you switch it around, what's behind? Or okay, this way. Okay, we flipped it, but it was originally like this, right, with the H forward. If you flipped B and C, so this is C, that's B. Now what's behind? The H. So then you wouldn't have to flip it. You would just do the A, B, and C. Does that make sense?
I mean, can you just do like the whole process again?
You could, yeah. I mean, I would recommend just doing these two.
Yeah.
But there, yeah, I mean, you can. There is that you can do, and then you can, yeah. I don't know, yeah. I would not recommend doing this the chain way, because I mean, unless you're really good with 3D models, you can actually see in front of you. I would just do it this way.
Did he ever teach any of this?
I don't think he did.
Yeah, I don't remember any of this.
No idea. It was on your worksheet. That's all I know.
Oh, okay.
It's on like
Every
every
person
process
has
does
got the
this.
hardness.
Wait, do you have the name? I don't think I've had the name of hardness. I guess you.
No, I don't have the names of hardness. Like the actual, like the words that they stand
No,
for.
no, no. I mean, like naming the compound. Like, I don't think I've had the name.
Oh, all you gotta do is just you indicate your stereo setting. That's all you gotta do. No, so you don't. In this case, you don't have to, but sure. Yeah, it's 2S. It's you're describing the stereochemical center.
Wait, we will only name it like this only if like they tell us to.
Yeah, only if you have a chirocarbon, they tell you that there's a chirocarbon here. Yeah. Yes.
Can we do one of the questions that are on the slides?
Sure.
It says like how many different tetramethylbenzenes are there?
Can I see which one?
Yeah. Like isomers?
Not this question.
Wait, did you guys do this?
Huh? It's just it's not a hard question. It's just tedious. But can I erase all this?
Yeah.
Tetramethylbenzenes. Is it tetramethyl, right?
Yeah.
Actually, that might be as good as yours. Okay, benzene. So I guess there's this thing. But I think have you guys heard of orthoparameta?
Yeah.
We talked about that?
I don't think he did he?
It was on
It was on the slides, but I don't
And
think he talked about it.
I think he expects us to know it's on
Yeah,
the
yeah.
slide, so as in red as well.
Yeah.
Oh, interesting. Yeah, so what he's talking about there with the whole tetrasubstitute benzene is now when you're talking about benzene substitutions, I can't believe I'm teaching this. There's ortho, there's meta, and there's para. So these are now indicated on the names of the benzenes. Okay? So ortho, this is not, when you do tetra, that's harder to do. So pick a center. I'm gonna pick one here, because they're equivalent, doesn't matter. So when something is ortho, it means it's right next to it. Right, so nothing is ortho to here. The next one is meta, which is 2 away. So we do actually have a meta. So this would be meta dimethylbenzene. And then if you had the one directly opposite, it would be para. We don't have it, but that would be para, the para segment. Okay. But to your question about the tetrabenzene, there's this isomer. It's just how many times can you move 4 methyls around? There's this thing. I don't know. I mean, you could, it's all there. I mean, let's see how many. Okay, there's at least 3. I think it's the same, isn't it? As this one. 3.
I can't answer yeah, but
there is no systematic way of doing it. You just kind of play around with it. All you know is from the name, there's tetra, there's 4 methyls on a benzene. So you just play around, place them all on the carbons. Because you can't have 2 methyls on a benzene, or on a benzene carbon, because that's already full. 1 methyl fills this octet. So you can't have 2 of them. So it makes it easier, so you can only have 1 at a time on 1 carbon. But at least I don't know any systematic way of doing it. I just kind of guess and checked, and it worked.
do you think there will be a question like this on the test?
No.
Oh, okay.
No. Yeah.
If we were to, well, would we be asked to name it? And then because like with the first example you gave, there's only one relationship, but then with this one there's a bunch. So
Yeah.
how would you know?
Good catch. Yeah, you wouldn't. You can only do 2 at a time.
Oh, okay.
So you can't. You have to do 1, 2 at a time. Makes sense. Any other questions? Yes.
Are these some structural isomers?
It's there's a really good problem on the discussion which actually deals with that. I just don't remember the name. I don't remember the numbers, but C8H18. Okay, so this is a structure for a normal. This is a structure for an octane. Okay. So that's just a shred of octane. Right? One way you can draw this is a shred of octane. Now, if you want to do more structural isomers, what you could do, I know Enderle has been taught, you guys were taught degrees of unsaturation. Have you guys been taught degrees of unsaturation? No? Okay, so I guess we're pigeonholed to just considering linear alkane. You guys, anyway, alright.
You never know.
Okay, so in this case, I mean, we were just doing linear alkanes. And the way I would do it is not just, it is basically guess and check, but 1, 2, 3, 4, 5, 6, 7.
That's 8.
Wait, this is not 8. 1, 2, 3, 4, 5, 6. Yeah, it's 7. Okay, anyway. What I would do is just pick another carbon and add a substituent, right? And so now when you count this out, right, there's still 8 carbons, but then there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 hydrogens, right? And then the next structural isomer. So this is 6. Now just take another one of the carbons and add it as a substituent somewhere. And now you have 6 carbons of your main chain and then 2 methyl substituents. and then you should get the same CH18. And literally just keep doing that. I think you only have 4 actually. 1, 2, 3, 4, and then 5. 1, 2, 3. And then that's it. If you do it the other way, then you would basically get this again. Yeah.
For the second one, can you put the line in the middle?
Like here?
Yeah.
Yeah. Doesn't
How do you know when to stop? Like if we're
once you start seeing that they're the same, they're gonna start looking equivalent.
okay.
Like this one for example, you can argue that if you placed this one in the middle, right? And you should have gotten what yours would have looked like is something like that. Something like that. And then this one is kind of like the final structure. So I guess what I'm saying is it doesn't really matter where you put it on, because eventually you're going to put it on all of them. Like,
It's just like if a question asks me like how many structural isomers are there, like I don't know when to stop like drawing them. You know what I mean?
yeah, no, I know what you mean. Again, there's no real easy answer to that. It's not like there's like a magic formula that tells you how many there are. You gotta have to keep drawing and seeing if they're identical. Because once they're identical, they're the same thing. So you don't have to count that as another one. That's just the same thing in a different orientation. Yeah. Yeah. Does that make sense?
Yeah.
Okay. Yeah. Okay. Any other questions? All right. Cool. I think the last thing I had. Oh, the last thing. I had a quick survey of reactions that I think are important for you guys to know. Trying to help you guys out so you guys want to study all the reactions and blah, blah, blah. So the first one is a hydrogenation reaction. Hydrogenation reactions, or I guess it's hydrogenations of an alkene. Can you say that? It's alkene. Of an alkene. Alright? So what happens here is you take an alkene, in this case we have propene. We take an alkene, we add straight up molecular hydrogen, and lo and behold, we get an alkane. So you literally just replace the double bond with hydrogens, and it becomes an alkene. This is a really cool catalytic cycle. You don't have to know this, I don't think, but you know, you can write it down, or you can write catalyst. There's also halogenations, which is where, again, you take an alkene, this is a butene, you add elemental bromine, it could also be elemental chlorine, it can't be fluorine, but it can be iodine too actually. And all you do is you replace a double bond with 2 Brs. Alright? 2 Brs. Yeah, that's called the halogenation reaction. Right. Now be very, these next 3 are going to be a little more interesting. Can I erase this really quickly? On the next one here, 2, that's 3. So now this is all about alkenes and alkanes. Sorry, one more alkene. So that was a hydrogenation. This is a hydration. A hydration of an alkene. Right? So what happens when you hydrate an alkene? Right, you add water to it, and then water can attach to it. That's a hydration reaction. Okay, so those are the 3 reactions for alkenes that you should know. Alkenes, alkynes. these next few are specifically for alcohol. So if you have a primary alcohol, primary referring to how many carbons are attached to the alcohol, right? If you have a primary alcohol, what happens if you oxidize it? Right? If you oxidize it, you get an aldehyde. And so we really, I mean, we skipped over that in lab, but basically, when you what oxidation means is that now you have more bonds to oxygen. Here, this carbon only had one bond, now it has two. So you've oxidized it, okay? And then something very similar, what if you have a secondary alcohol? So remember, this is primary. What if you have a secondary attached to two carbons? Same exact process, you get a ketone. Okay? Okay. Does that make sense? So these are the five I think are pretty important. Yeah.
What are they called? Or like, what is the process called?
Like these two specifically? I would just call them oxidation of alcohols to whatever. So this would be oxidation of primary alcohols to aldehydes, and this is called the oxidation of secondary alcohols to a ketone. So they're specific, right? You can't, if you want to oxidize, you can't oxidize a primary and get a ketone. They can only do one. If it's a primary, it'll always be an aldehyde. If it's a secondary, it'll always be a ketone. All right. Any final questions there? Yeah.
What about like a tertiary alcohol?
You can't.
Oh, okay.
Yeah, you cannot do that. Which I talk about, but I doubt it's gonna be amazing. All right. Any other questions there? Okay. Sick. All right. That's organic chemistry. All right, you guys know everything now at this point. Okay, cool. All right, I have 4 more chapters to go. So, what's next? I have Nuc Chem is probably the most. It's the most diverse. The kinetics one's actually pretty easy. And the crystal field theory is going to be fast. Anyone have a preference? Kinetics, anything? Nuclear? Yeah.
It's like the most percentage and organ. It's not like the distribution.
Oh, yeah. So Nuc Chem. Nuc Chem is interesting. Nuc Chem is physics, but whatever. Alright. Go, can I reset or go with that? Yeah, I don't know. I've been trying to read up on a lot of nuclear stuff actually. I find it pretty interesting. Did anyone watch Oppenheimer?
Oh, I did.
Yeah, did everyone watch Oppenheimer? It's a really cool film actually.
I fell asleep.
Damn.
It's too long.
All right. I can't believe you said that after I turned your grades. That's a lot.
I fell asleep. He was honest.
Yeah?
It's super loud. I don't know how you can sleep.
No,
It's
no.
like so.
Like the middle is like an hour of nothing happening, you know?
It's like a big explosion.
Yeah. I mean, last hour was interesting, but like the middle hour is like
It's just
like
explosion. Okay, anyway. But yeah. Nuclear chem. Okay. So with nuclear chemistry, it's important to know vocabulary. Vocab is important in nuclear. Okay? So this is problem 1. Well, we don't have to do that formal. What's a beta particle? Yeah, it's an electron, yes, but why is it an electron? Or I guess I suppose let's kind of expand on that definition a bit more. So it's a specific decay where a neutron is converted to a proton, whereby it releases an electron. Right, so it itself isn't an electron. The actual process is a neutron becoming a proton, but what's released from that reaction is an electron. Right. And then the little symbol you can use is all right. So what about alpha particles? It's where a nucleus, it's a type of decay again, a decay where your nucleus releases a helium atom. Okay. So these kind of decays are seen when your isotopes are very, very large in mass. Right, and then they start decaying, and instead of going by beta particles or positron decay, they really want to release a lot of those neutrons out, so they release alpha particles. And the symbol you want to use for alpha particles is that 14 helium. Okay. The next one is something similar to beta particle emission, but you have something called positron emission. Right, so a positron, it's again a decay where protons are converted to neutrons. So I'll actually talk about why these are cool, but notice really quickly, these are the opposite. And there's a reason why they're the opposite. And a positron is described like that. If you're ever interested in particle theory, amazing, amazing stuff. It might put you to sleep though, I'm not gonna lie, but it's cool stuff. All right, another one. Something called electron capture. Okay, so this is not a decay. It's actually a specific type of. It's not a decay. It's where an electron is captured by the nucleus. It's where an electron is captured by the nucleus, turning a proton to a neutron. Right? So these four processes are the most important ones to know. Right? And being able to differentiate between all of them is also very important. Right? So specifically why I did this is because I want you to focus on what's happening to the neutrons, what's happening to the protons, what's happening to the electrons, okay? That's why that's there. All right. Just because I put it in my notes. Neutron to proton. This is the beta particle emission. Okay, and then proton to neutron happens with electron capture and positron emission. This is just a condensed version of what I wrote down here. Okay. Cool. All right. Make sense? All right. Can I erase? Everyone cool with that? I think we can. And then these notes will be posted also. So there's nothing. All right, now we're going to do some simple nuclear equations. This is number 3 on the homework. So it's asking us uranium-238 goes through alpha particle decay. What else do we get? Okay. So in this case, what alpha particle does is you should immediately look at the number of protons. Okay, so we know the number of protons. We started with 92. We lost 2. So how many should we have? 90. All right. Again, we can also look at these atomic mass numbers. We started with 238, a number of nucleons. We lost 4. So now we have 234 number of nucleons. And then all we're missing now is the actual element. And by cross-referencing the periodic table, asking which one's element 90, it's thorium. Okay, so what's missing is thorium, 234 thorium. Okay. Thorium is actually a safer version of uranium, but big government doesn't want you to know that. You have 234 thorium. Okay, now for B, we're looking now at something else. So we have 234 thorium. That goes into 234, 91 PA. No, didn't look that one up. This is the element that's right next to thorium. So the question is, what are we missing? Well, notice that the number of nucleons stay the same. So the number of protons and neutrons stay the same. But what changes is the number of protons. Right? So in the number of protons, there's only one technique where we don't change any number of neutrons and protons, but we get an extra proton now. Right? This went through beta particle emission. Right? The neutron became a proton, where we added a proton. So this is a beta particle emission, and so it's important. Oh, they really like that, I see. That we describe it as such. So it's important to understand, or the whole reason why I went through the whole nomenclature about it, is because it's important to know that this is a beta particle emission process. All right? So far so good? The only other one that we want to kind of cover is what happens instead of a beta particle emission, which we know that the protons get larger. What does an equation look like if the protons get smaller? Right? So what happens if it goes through electron capture or positron emission? So this is actually number 7 here, where we do number 7a talks about an electron capture reaction, where we take 68 gallium. Okay, so 68 gallium. Okay, the problem tells you it goes through electron capture. So this is one of the only ones that isn't a decay process. You actually get an electron. You add an electron. And what happens is this electron helps convert a neutron, it helps convert a proton to a neutron, giving you 62. Oh, it's because I'm looking at the wrong one. 68. But we lose a proton 30. and that becomes zinc. Alright? So when you talk about electron capture, you look at the number of protons. If your number of protons decrease because the proton became a neutron, then you're either dealing with electron capture or with positron emission. Right? So, yes, knowing your chemical reactions means, yes?
Doesn't electron capture also like produce gamma rays? Question mark?
I was not under the impression that was exclusive to it. The thing about gamma rays is they're not important to the chemistry. That's really why I kind of omitted them, is they're not, I mean, they might, and I just don't know, but the gamma rays themselves are not important to the chemistry. Yeah. They're just, because they're not particles themselves. That's just light, high energy light. Does that make sense? Okay. Any other questions? Go ahead.
Is that, I use it. It's your choice.
Oh, yeah.
So I feel like about
No,
that. Thanks, bro.
Okay. Sorry. Oh, yeah.
Wait, so then should we write in the gamma ray just in case, or no?
Sure. Yeah, I think you should. Yeah. I just, I don't know how you would write a gamma ray.
It's like a
Is it-
it's
is
like
it-
curly O.
Y0.
It's like, I draw mine like, I think it's a gamma, right?
Like a
It's
capital
gamma.
Y.
It's gamma, or letter.
If it's like gamma naught?
Like a capital Y.
Like
You know,
capitalized?
Yeah, like it's a
Yeah.
curly capital Y.
You know, like.
Yeah, yeah.
Why?
It's like somewhere between.
It's like a fancier Y, it's like-
Yeah, like the A's are a Y.
Yeah.
Just put a Y, Brad.
Yeah, Y, yeah.
Okay. All right, cool. Sick, guys. Okay. Finals is so much fun. Okay, makes sense though, everybody, yeah. Simple as that. I'm glad the Y was a point of contention here. All right, all right, the next part is, so this is the reaction which you're also going to be expected to know, right? What kind of reactions are going to be possible in sort of nuclear systems, right? All right. Race, can I do that? Yeah, I'm good with that. All right, so now we move on from nuclear reactions to decay kinetics. Decay kinetics. So, the most important point is all decay kinetics is first order. Okay? All decay kinetics is first order. And so you can use first order that you learned in reaction or in kinetics to describe the different reactions that are going to be happening in your systems. All right, so this is number, the one I kind of wanted to do is number 17 on your post-chapter assignments, where it talks about americium. 241 is used in smoke detectors. The half-life is 433 years. It decays 433 years. It decays by alpha particles. How many alpha particles are emitted by a 5-gram sample of 241 americium? All right, so when you're given a problem like this, again, when you're given a half-life with decay parameters, the first thing you should think of immediately is, can I get my K? In nuclear physics, that K is known as your decay constant, which I think is described sometimes as lambda, but it's K. It's just a different name. I don't know. People like feeling important sometimes. Okay, so in our problem, we found that the half-life of AM241 is 241 AM. Let's do that. Is 433 years. Okay. So what you could do here, you can do one of two things. You can either input 433 and keep your K in terms of years, but the problem asks how many alpha particles are emitted per second, right? So what that's going to tell you is you might want to just convert that to seconds and then just plug it into here, right? Just take the time to kind of get ahead of the problem here. So that's what I did. You know, you have to convert 43 years into seconds. Do you guys want me to show you how I did that? Or you guys want to just give the answers?
Yeah, just answer.
Just answer. Okay. For this one specifically, it's going to be 1.3655 times 10 to the 10 seconds. Okay. So you just do a whole bunch of different conversion factors to get from years to seconds. All right. All right. So this is how long the years is there. And we get that K, let me plug this in here. We get that K equals 5.074 times 10 to the negative 11 seconds inverse. All right, so now we have a K, which now helps us get into a whole bunch of different other things. All right? Okay. All right, cool. So when you're given something like this, we now know how much, with the kinetic rate constant, we just know, all we know is that time, we only know a time parameter, so we need to get an amount parameter, because it's asking how many alpha, I think something about alpha particles, how many alpha particles are emitted by a certain gram of this compound. So step 2, we need to actually find the number of atoms, right, which the number of atoms is a direct proxy to the number of alpha particles emitted. Right? It's an indirect measurement, but it means the same thing. Right, so the number of alpha particles, which is now described as the number of atoms. Right, because all atoms will emit an alpha particle. Right, so we take our 5.0 grams of 241 American. We multiply by the molar mass. In this case, the molar mass is implied to be the atomic mass number. So 241 grams in 1 mole of AM. Okay. That's going to give us a total of 0.02075 moles. Then we take the number of moles of our americium and turn that into atoms. And I have not seen that calculation since 2A, but it's the moles, 23rd, when 1 mole there's 6.022 times 10 to the 23rd atoms. That's Avogadro's number, which then is 1.249 times 10 to the 22 atoms. All right. Okay, so then the final step here, we have some amount of stuff. We have the time parameter. All we have to do then to get alpha particles per second is to multiply them both. So 5.074 times 10 to the negative 11 seconds inverse times 1.249 times 10 to the 22 atoms, right? Which at the end is going to equal 6.34 times 10 to the 11 alpha particles emitted per second. Does that make sense? Does that make sense to you? You good with that? Cool. Okay. Any other questions? We were kind of going to do another one similar, but more application based. But does anyone have any questions? Yeah.
Wait, so you're saying atoms is alpha particles?
Yes, because every atom releases that alpha particle.
Oh, I see.
Yeah.
Yeah.
That's it's like a proxy name basically.
Yeah.
Cool. Carries. All right. The next one is going to be more of an application-based question of this, which may or may not be obvious when you see it, but it's something that's actually pretty important, not only in science, but a lot of people get confused with this one. Okay, so now we're talking about. So this is question number 19 on your homework. Radioactive copper-64. It decays with a half-life of 12.8 days. Right? So question A is we have to figure out the half-life, which is going to be pretty easy. But then B asks us actually, for the sake of time, this one does the job too. Skip that. We'll do number 27. This is another kinetics problem. All right, so 27. This one is much more application-based. All right, 27. This is where you have a Rembrandt painting. So I guess how the question was asked is, okay, you go to a yard sale and you encounter a painting, and you think it's an original Rembrandt from the 1600s. How can you prove it? Something like that. Okay. So I call this the Rembrandt question, number 27. Remember that period of time that you're talking about. The Rembrandt's one of his golden ages was 1672. Okay, around that time. And what it's asking you ultimately is about carbon dating. Okay. So the activity of living wood, the carbon-14 activity, is 15.3 counts per minute per gram. Right? But your painting, the painting you would think is a Rembrandt, its count is 15.1 counts per minute per gram. Okay? And then the final piece of information you're going to need is a half-life. So the half-life of carbon-14 is 5,730 years. Okay, so these 4 pieces of information. So at the end of the day, yeah, this looks like a different application. It looks more difficult than what you would be encountering in a kinetics problem. But at the end of the day, this is just a simple kinetics problem, right? Where the activity that's like of your, in this case it's living wood, or it can be your activity of a fossil, it can be whatever activity it can be whatever activity. This is going to be your A naught, right? This is like your reference. Your A naught is your reference, and then whatever you're considering, so in this case it can be a painting, it can be a rock, it can be whatever you're trying to consider, that's going to be AT. Alright? And then of course half-life is half-life. Alright? But at the end of the day, this is what you're measuring because it's decaying. Right? The reason why we use radioactive carbon dating is because isotopes decay. And we can actually trace back a mathematical way to determine how long ago, how many half-lives have passed since this is decayed. All right, so as I was saying with A naught and AT, and of course that we know that this is a first order kinetics. All decay processes are. We can use the integrated rate law. To determine a few specific parameters. All right. So, we already know our A naught, it's 15.3. We also know our AT, it's going to be 15.1, but it's asking us to determine whether or not this can be from the 1670s. And so our time is what the variable that we're looking after. But for K, we don't have a K. But it's easy to find a K, because all we need is the half-life. Okay, so using this equation, we can use this one first if you want. We know our half-life in years, T1 half equals ln, no, well, we can just switch that around. ln of 2 divided by 5730 years. Okay. And once we solve that, we're going to get 1.2097 times 10 to the -4 years inverse. Alright, so that's our K, which we can now plug in here. Okay. So then at the end we get ln 15.1 equals negative 1.21 times 10 to the -4. We get our t-value and then ln of 15.3. Does that make sense? Yeah. And then we get that t equals 109. 109 years. So, this is saying that at the decay that we have, at 15.1 decay, it's only been around for 109 years. So the question is it a real Rembrandt? It's not a real Rembrandt. Okay, so it's 109 years. All right. The reason why I bring this question up, right, is this question can be asked multiple different ways. In this case, we already had a painting, so we knew what our decay was going to be. But what if you had years instead, and then you had to find out how much it's been decayed, and from there determine whether or not it's a Rembrandt or if it's a fossil or whatever you're talking about. So the interpretation here is that if your painting or whatever you're talking about has decayed more than you expect, then it's older than you expect, right? So if you say, oh, this painting is 99 years old, but you got 109, then it's older than what you think, right? It's 109 years instead of what you think 99 years, right? So it's an important consideration, but this question is, I think, really cool, and you'll probably see it like this. Hint. Your question.
Like, even though that the half-life is in years, it doesn't matter when the carbon activity is like counts per minute per gram.
No, it doesn't matter. Cool. Okay, all right. All right. See, okay. Everyone cool with that? Can I erase that? Okay. Yep. So, this is a particular question there. Okay. Okay, well, this is where, okay. So 57. Now we're moving on to another part of nuclear chemistry. So that was kinetics, the kinetics of decay. Now we're going to talk about energetics, specifically how we can use Einstein's equation to model our world. And so specifically in energetics, question 37 is it's talking about that one of the most stable, actually it's the most stable nucleon is iron 56. Right? Iron 56 is the most stable nucleon. Right? If the atomic mass of this thing is 55.93494, calculate the binding energy per nucleon. for iron 56. Okay, so now we're looking at energetics. So when you get asked a question that relates atomic mass and energy, the one thing you should immediately think of is I need to calculate a mass defect. Right? So mass defect. So at the end of the day, a mass defect, also called a delta M, is the understanding that you actually lose mass when creating this. The mass of the individual components is not the mass that you get of the total nucleus, the total atom. Okay, so first thing I want to do, well, let me just write down the formula first. It's the mass of the parts. Mass of parts minus the mass of parts minus mass of total. The mass of total is given to us usually, so we already know what that number is. But we now need to calculate what is the mass of our parts, of our individual components. All right, so you first want to identify your components, obviously. So iron 56 can also be written like this. We have 56, 26 protons for our iron, and then we have iron itself. So that tells us we have what? We have 26 protons plus 30 neutrons plus 26 electrons. Okay. Those are all our components. And now we need to calculate the mass according to these numbers. So for our protons, we're going to have 26 times 1.007276. These are in units of U. Okay, atomic mass units. 30 neutrons times 1.008665. That's the unit number for neutrons. And then 26 electrons, 0.00054848. Again, this number may seem small, and it is small, but electrons can add up. Okay. So combined, we get a total mass of 56.463 U. Okay. All right, cool. So now we got this number. All right. So now we can do we can find the mass defect, which is going to be 56.4634 minus 55.93494, and that's going to give us a total of 52845 atomic units. Okay. Cool. All right. But now we got to take our mass defect and apply Einstein's formula. We got to actually now relate mass and energy. So there's a lot of different ways you could do this, but I'm going to teach you probably the longest way, and it's because I want you to see where I'm getting my units from, right? Because we're trying to solve it in nucleon, I think energy per nucleon. But there's also different ways, different units of energy you can find stuff in. Right, so we're going to take the U that we have, and we're going to turn it into kilograms. Right, we actually have that ability, because this is an atomic mass unit, so we can just turn it into kilograms. So this is given to you on the exam. In 1 U, you have 1.6605 times 10 to the negative 27 kilograms. Okay, that all in all is going to give you 8.7748 times 10 to the negative 28 kilograms. Right? And now from here we can actually plug it into Einstein's formula, right? Because now we have the mass component, and then the c squared is our meters and time component. So energy equals delta M c squared. Okay? So we can plug in our delta M here in kilograms to get 8.7748 times 10 to the negative 28 kilograms times 3.00 times 10 to the 8th meters per second squared. All right. Okay, and then that's going to become 8.97345 times 10 negative 11, okay, joules per nucleon. Yeah.
So is the formula E equals mg squared or delta m?
The original formula is just m, but it's but we're expanding it to include mass defect.
Oh, I see.
Yeah.
But it's like, this is given that the change is going to be positive, right? It's like a mass.
Yeah. Well, I mean, yes. So it's
The
not
energy wouldn't
implied
be
that it's
negative.
it's not implied that it's positive. It's understood that the mass of the parts will always be more than the mass of the total. So does that make sense? So it'll always
Yeah,
be
so
positive.
it will be, okay,
It'll always
because
be
it wouldn't
positive.
make sense if it was like negative.
Yeah, exactly. Yeah, it would be always positive. Yeah.
When you're like multiplying the proton and neutron, like those numbers with the unit U, where did this come from?
Those are quantum mechanical calculations. Where they come from specifically is physics.
Mhm.
Where they come from on the test
Yeah.
is on the back part.
Oh, it's on the reference.
The reference.
Okay.
Yeah, so you will see these equations on there. You'll also see this one and your conversion factor. You'll see all those ones.
So I think in our, I did like the problems were like instead of working in like U, we worked in with like grams. And like in that case, we will have to divide by like 56 to get the joules per nucleon.
Yes.
So like, is it because we are now working in grams that we don't have to do that? Like we don't have to divide by 56.
Yeah, so so by dividing by 56, you did it over here, right? This is where you kind of convert into your grams. I'm instead converting to grams here.
Oh.
It's just two different places, but they're both mathematically correct.
Okay.
If you are comfortable working with grams that way, go for it. I like doing it here.
So if I were to work with gram, will I use the same mass for proton and neutron? Right? But I just instead of U, I say it's gram.
Only if gram is given to you. From what I've seen on your reference sheet, it was U.
Oh, okay.
But yeah, okay. Makes sense?
Yeah.
Yes.
I thought after you find the energy, like it's joules over nucleus, and then you put one nucleus, and then you put like how many nucleon there are. Aren't you supposed to divide by the number of nucleon?
Oh, yeah, we're not done.
Oh, okay.
Yeah.
Okay.
Yeah, so we're here, we made it here. But yeah. Any other questions relating to like this part? Okay, so, all right, so now what we want to do here is we have right now in joules per nucleon, but what we want, I didn't specify. We want the units of energy to be in kilojoules per mole. All right, so how do you go from joules per nucleon to kilojoules per mole? Obviously, the kilojoules to joules part is easy to do, easy enough. And then go from nucleon, which is it's just a quantity of stuff, to go from some amount of nucleon to moles. We would need to multiply it by Avogadro's number. Nucleons in 1 mole of nucleon. And that's going to give us 5.40 times 10 to the 10 kilojoules per mole. Does that make sense? Okay. So again, like to Wayne's point, I only saw them in use.
Yeah.
And I did see this calculation, this unit conversion. There was another one that can take you down a different path. It's the same exact stuff, it's just different units now.
Yeah.
But it depends on what units you're asked. Or you're asked for.
And that's on the equation sheet, right? Like the conversion.
Yeah, that's something we should. Yeah.
I thought the energy that you get from the equation was joules per nucleus though. I didn't know it was,
I mean, it is.
like, why didn't you take into account the nucleons?
Oh, I did.
I feel like normally I'm used to like, aren't you supposed to put like 56 nucleon and then divide by nucleon?
You're supposed to usually.
No,
But that might.
sheet. No, if
But
you
that
Should we
might.
just do this instead?
I'd say so.
Okay.
But usually it's like, isn't it usually like 6.022, like, and it's like atoms?
Yeah, but yeah, it is
But
usually.
they're
that.
interchangeable, I guess.
Yeah, it's just because nucleons are also not atoms, but they're just an amount of stuff, right? 1 mole of nucleons is 6.022 times 10 to the 23rd amount of nucleons. Yeah. That makes sense. But yes, to your point, yeah, you do usually do that. All right. Any other questions? That's a Rembrandt question. Okay, this is the last page then. Last topic. Okay, cool. Alright. Everyone good with erasing? Everyone good with that? Yeah. Alright. Alright, the last part here involves, so this time we're going to go skip all the way back to number 12. Now we're going to look at predicting stability. Predicting stability and decay modes. So for light, so I guess for number 12, you can kind of give context. Iron has 6 different isotopes. Okay, it has 6 stable isotopes, and it has 2 radioactive isotopes. Okay, these are my radioactive ones. The thing though is we need to predict, we were kind of told if it was radioactive. Anyway, we need to predict what mode it's going to decay in, right? So, for lighter nucleides, or nuclides, right? So we're talking about protons less than 20. Yes. No. Much better. Okay, so nucleons with protons less than 20. The most stable ones you're going to get is when your ratio of neutrons to protons is 1 to 1. Alright? With heavy nucleides, that gets a little more vague. So, anything now above a 20, so it's not equal to, right? Typically, now we're allowed more neutrons. The accepted value here is technically 1.5, right? But this is not like a hard and fast rule. Just because you have 1.5 to 1 ratio doesn't mean you're stable, and then 1.4 is not stable. This just means that for heavier atoms, you just need more neutrons. All right, so that kind of begs the question here, right? Using this information, can we predict how things are going to predict decay modes? Can we predict how things are going to decay? Right? What kind of processes are going to happen? All right, so if you have too many neutrons, if you have too many neutrons, you're gonna likely decay by a process that turns your neutrons into protons. Right? So this is where we're gonna do beta decay. Right? Where we take neutrons and turn them into protons. Right? Now, what if you have too many protons? Well, you'll most likely then you decay by a process that takes our protons and turns them into neutrons. So we have electron capture as one process, or positron decay. Now, both of these things are plausible. And then if you have a extreme amount of both, doesn't really matter. So these are typically really heavy atoms. So we're talking lanthanides, like group 7S's. If you have extreme amount of either, it's gonna decay via the alpha emissions, alpha particle emissions. Okay. Alright, does that make sense, everyone? Yeah. So now going back to these guys, can we predict their modes of decay? Alright, so for 53 iron, we have 26 protons. Oh, I don't have the number there. Okay, we have 26 protons and 27 neutrons. Yes, although technically we do have a larger ratio. This is where I'm saying it gets kind of dicey, where this is close enough to have too many protons. Right? This is basically one above, so essentially this kind of means it's a 1-to-1 ratio. It's a 1-to-1 ratio for a heavy atom. So this will decay via too many protons. So this will decay. I don't know. I think positron would be the more safe bet here. So that's the positron emissions. And then here it's going to be 26 protons. 26 protons, and then what? 32 neutrons. 3 neutrons. This now has a lot more neutrons. So this will probably decay by beta decay, or beta particle decay. Right? The last comment I'll make generally about nucleon stability is that 56 iron, again, like I said, is the most stable isotope, or most stable nuclide. Okay? And then even refers to the number of protons and neutrons is more stable than odd even and odd odd. Odd even and odd odd. You are given the magic numbers on your reference sheet. All right. Any questions on nuclear chem? Cool. All right. Cool. All right. Any other questions? Can I erase? Yeah.
What about fission and like bombardment?
They will only, in what sense?
Just
in general?
Yeah.
Yeah. You won't be, from what I understand, you will not be tested on like the actual like industrial process of fission. You'll just have to know what they mean, right? So So bombardment typically, you know, when would you use bombardment? I guess is my thing. Like, when's the application of bombardment? Is it typically you take something and you bombard it with something else, and that creates a heavier ion, typically, right? And then fission. This one I always get confused with nuclear fusion. Fission is also coming together, right? Fission is no, that's fusion. So fission's reverse. Yeah, fission's reverse. So in fission, you can take a heavier atom and it breaks away. I suppose it breaks apart. So they fit in the precipitate in atomic fission. Yeah. That makes sense.
So bombardment is making a heavier one and fission is making a smaller one?
Yeah, that's a good way to look at it.
Like, do they still need like decay, like particles, like
You can, decay is somewhat synonymous with fission. Fission is also more typically used for like hydrogens and heliums, but they mean the same. Okay, any other questions? Oh, yeah.
Is there like exceptions to the rule for like if something is like it's like the rules are take place but they're not stable? Or is it the other way around? I'm pretty sure there's some exceptions.
I don't. Well, here's the thing. This whole process, the whole thing about predicting stability and decay models, are all pretty wishy-washy in the first place. So yeah, there are some exceptions. However, what you'll be seeing, the exceptions that you're going to see are, they're not like. What's what I want you to look for? You will not see an exception be an answer. The answers will abide by the rules.
100%.
Yes.
Alright.
Cool. They'll abide by the rules. Alright?
Alright. Cool.
Hey, anything else? Nuclear chem, nuke, nothing? At the very least, I want to get through kinetics, because there's an example there that I really like and I think you guys should look at.
Are you gonna do mechanisms?
Yeah, kind of.
Okay.
I think that is a mechanism, but
It's like the hardest.
that is a mechanism question. Alright, everyone ready to move on to kinetics? So kinetics is one of my favorite branches in chemistry. The 14-page paper I had to write this weekend was all about chemical kinetics, which was interesting. So, I understand your pain, unfortunately. Let's see here. All right. All right, so a few key details I want to go with kinetics here. Kinetics. Before we move on, Daniel, is this still going?
Yeah.
I have more space than I thought. All right, cool. All right, one of the most famous processes of all time is called the Haber-Bosch process. Haber-Bosch process revolutionized the world by turning atmospheric nitrogen, combining it with elemental hydrogen, and turning it into usable fertilizer. Basically, allowed people to farm pretty much anywhere. Of course, some exceptions, but it's a cool process. Fortunately, it's not sustainable, but all right. So the question here, this is actually question 13 on your homework, and it was asking what is the relationship between ammonia production and H plus consumption, or it's not H plus, it's H2 consumption. All right. So, in a general sense, when you're talking about kinetics, you're talking about the rate of something disappearing is directly equivalent to the rate of something appearing. Okay. So, very simply, the relationship is. You guys probably saw this. Right, so this is the kinetic, this is a general rate law of a, this is general rate law of a reactor, right? We have the change of a reactant, the change in molarity, over the change in time, times 1 over its coefficient, And because it's a reactant, it's going to negative, right? We're losing concentration because it's a reactant. But that's directly correlated to the appearance of the product. Alright. So those two processes are interlinked. The disappearance of the reactant is the appearance of the product. Okay? So this is just general kinetics. But yeah, okay. Any questions there? Great. I think this was on the second midterm actually. You should review that.
Yeah.
Yeah. I think the first question was this one. All right. Good. All right. So the next part that I want to mention here is number 14. Right. Again, this is just a very fundamental kinetics thing, right? We need to know. In this question, they ask us to write a whole bunch of stuff, and we want to express the units in a whole bunch of different things. But the reason why I want to bring this up is because the units of your reaction, or the units of a reaction rate, will always be concentration over time, molar per second. Okay, always. But now we have the kinetic rate constant. Those units will change depending on our situation, depending on our scenario. Okay, so for all k's, you want to identify overall reaction order. You want to identify your overall reaction order. Then subtract x by 1. You'll actually see an example because this was poorly planned out. But what does this mean? Well, we have k equals 1 over molarity x times some sort of time inverse. Okay, so this is the general equation for the units of k, always. Right? Where we have some sort of time inverse, it'll always be there. And then we have some molarity to the x power, depending on our overall reaction. Right, so we can start off, first off, with our, let's say, whatever we're talking about is zero order. Okay? Alright, it's zero order. So again, like I said, we want to subtract x, and subtract the overall reaction order by 1, which then equals x. Okay, so let me rephrase. We want to identify the overall reaction order, and then we want to subtract the overall order by 1, and then that's going to be our x. So our overall reaction order for this reaction is 0, right? So 0 minus 1 is negative 1, and indeed, should have probably not a circle with this one. Alright, so I'm probably didn't want to say. Okay, anyway, this is a bit more confusing, but basically because m is already underneath, it already gets a negative x. So negative times negative 1 is going to be positive 1. So indeed, for zero order, it's actually m divided by s. That's our zero order k. It makes more sense though if you do it with 1, right? If you do a first order reaction, okay, if you do minus x, what's 1 minus 1? 0, right? So you put 0 where x is. So then this cancels this whole thing out, which leaving us with k equals inverse seconds, which is true. Right, so no matter what overall reaction you have, just subtract by 1, and you should get your units of k. The reason I bring this up is because depending on the units of k, you can already tell what kind of reaction order it is. So let's say instead of giving you a reaction and telling you to find the k, what if they give you the k and you're supposed to imply what reaction it is? Right? That's something to watch out for, I suppose. All right. Okay, cool. Any questions there? Alright, these next two, well, we're gonna do one initial reaction order, and then we're gonna do one mechanism question. Yeah, okay. Okay, so 22 is also in your homework. I picked this one because it's a biochemistry question at the end of the day. So we have a protein called hemoglobin, which binds our oxygen, which helps transport oxygen through your body. And then we have the concentration of carbon monoxide, which actually binds irreversibly on hemoglobin, which is actually why carbon monoxide poisoning is super dangerous, because you literally suffocate from the inside. And then you have some initial order. Okay. So I told you to mark my words. This sort of table stuff is not going to go away. All right. But the one thing that at least I was talking with some Enderly students is it is the possibility that you can get a fraction. It might not always be nice and was first order or second order or whatever. Sometimes you might get some fractional stuff in there. Oops, that's not 0. It's 1. 1, 2, 4, 7. Okay. Alright. So now we have the table, right? So our job is to find the reaction orders for both things, for our hemoglobin and our carbon monoxide, and then find the overall reaction order. So we gotta find our reaction orders. All right. So first off, the question or the general equation that you want to use is the concentration of A for trial 2 over the concentration of A trial 1. This to the x power being our reaction order. That's going to equal the rate of 2 divided by our rate of 1, trial 1. Right? So this equation is not given to you in the reference sheet. All right, cool. So now we have to figure out, what is our stuff. So, let's do that. I'm going to choose hemoglobin first. So, when we're looking at this table and we're trying to find the reaction orders, we want our reactant of interest to change, right? So if I'm looking at hemoglobin, right, these two reactions we don't want to consider because hemoglobin doesn't change. We want hemoglobin to change. So 2 to 4, so these guys are good. But then we also want to make sure that all our other reactants, it could be more than one, are constant at these two also. And so they are, which is great. So we can use experiment 1 and experiment 2 to look at the reaction order for hemoglobin. So reaction 2 would be 4.42 divided by 2.21. Our initial reaction here is going to be 1.24, 0.610. Okay. And then if you do the math on this, you'll get 2 to the x power equals 2. So what does x have to equal?
2.
Yeah, 1. X equals 1. Okay, so it's a first order reaction. Awesome. Not too bad. Okay. Now for carbon monoxide, right, we do the exact same analysis. We want to choose 2 experiments where carbon monoxide is the same, and then, we want to choose 2 experiments where carbon monoxide is different, and the other reactants have to stay the same. So instead, now we want to look at experiment 2 and 3. All right, so to do the same analysis here, we do 3 divided by 1.0 to the x equals 3.71 divided by 1.24. That's going to give us a 3x to the third which again is x equals 1. Alright, so when it's asking us to find the reaction orders, here we are, we found them. But now we also want to find out the rate law. We want to write a rate law. And so now we can just write it pretty simply. Rate equals K times hemoglobin to the first power times CO to the first power. That's our rate law. And then from there, it might ask you to find the K, it might ask you to find the rate, but we know how to do that. All we gotta do is just plug and chug. Right? So we know the rate, we know the concentration of HB, and we know the concentration of CO. Let's just try experiment 1, and you'll find K, just by plugging those numbers in. And then if it asks you, what if I had this concentration and this concentration, but I don't have an initial rate? Well, now you know the K, and then you just plug in your concentrations, you get your rate. All right. That's what it is. All right, cool. All right. All right. Before reaction mechanisms, just one last time here. So this next problem is question 31 in your homework, where it asks us, we have this reaction. A goes to B, right? Where we have that A naught equals 2.0 times 10 to the negative 2 molar. Okay, and then it tells us that a ln of A times V, or versus time, my bad, sorry, versus time. They plotted this, okay, and they got a straight line with a slope of negative 2.97 times 10 to the negative 2 inverse minutes. Right, so you should immediately, right, as of now, I mean, obviously, you know, it's okay if you don't, but I don't know how it's okay it is if you don't, but ln of A versus time, that, and you get a straight line with a slope. There's only one reaction order that you can be. It's first order kinetics. Okay. If you have 1 over A versus time, right, that's second order. And then if you have just regular old A versus time, that's 0 order. Okay. This is just making sure you can kind of jump from different things and kind of tell you on the graph here. So just by their information telling us what our plot is, we already know it's a first order reaction, which is awesome because now we know that if it's first order, it'll look like this. Right, that's our rate. Another thing to keep in mind, just because this is just one molecule, you might think, oh, it's unimolecular. This A wasn't given to us. So this could be 2, this could be 3, and then it gets much more complicated. So anyway, but first order, now we know for sure, okay? So we actually do know our K. Well, let's kind of stress this out real quick. Okay, so this is the integrated rate law for a first order reaction. These I think are given to you on the reference sheet. You might want to check on that though, but I think they are. But anyway, but that's the only way that you can plot ln of A is if you plot it in this relationship. And so this relationship gives us, again, the mathematical relationship, y equals mx plus b, where m is negative k. So we actually already know our k. It was given to us in the problem, just not directly. And so our K is actually positive 2.97 times 10 negative 2 minutes inverse. So we know our K. And then the problem simply asks, find the half-life. It's not too bad, right? The half-life of a first order reaction is given to us by the equation T of 1/2 equals ln of 2 divided by K. So we take our K from here, plug it in, T of 1/2 equals 23.3 minutes. that make sense, everyone? Cool. And then obviously keep in mind that this kind of problem is just it's a simpler version of any problem you can do with this now. Because, yeah, I mean, that's pretty much it. I did want to mention no, I think I'm cool with that. So, all right, cool. So does that make sense, everyone? Yeah. All right. Now comes the mechanism stuff. This is fun. All right. Okay. Anyone know if Dutch Bros is open late? Alright. Okay.
Yeah, they close at 11.
Holy shit.
Hey. Alright, cool. Alright. Okay, cool.
Just look forward to it.
Okay, so now we're gonna start talking about mechanisms, which arguably can be the most complicated. Alright, so mechanisms. Alright. So this is number 61 on the homework. And it's asking you have a equation here that is modeled by this stuff here. It's going to be a rough one here. This is a fast step. C4H9OH2 plus water gives us C4H9OH plus H3O plus, and this is a fast step. Alright, give you a second there to catch up. Okay, so we're given this stuff here, right? So this is asking two simple questions. Write the overall reaction, and then give me the intermediates. That's all it's asking. But this is a good jumping point, because the next problem obviously we'll do an actual mechanism problem. But these two processes you should always do for any mechanism. Figure out what's your overall, and from your overall, figure out your intermediates, because they determine a lot about your reactions. All right, so on a quick point, it's important also that you identify your slow step. Because your mechanism, at the end of the day, your mechanism is described by the slow / rate determining step. Right, so so when you're looking at, what mechanism do I use, you should always look at your slow and then describe your reaction based on your slow equation. Right, so what that tells us is we actually also know our overall rate law. What is our overall rate law? Well, so we go to the slow, so this is our slow step. We just look at the reactant. That's it. Not too bad. Right? The reactant for the slow step is just C4H9Br. That's it. Right. And then we can name this K1 if you want. And this K2, this K3, so we don't get confused later on. Right, not too bad.